In this chapter we are going to discuss one of the most important topics of any testing course, test design techniques. So what does we mean by a test design technique, or why do we use one? By test design technique we mean the process through which we identify what to test and how to test that thing efficiently. Before we can actually execute a test, we need to know what we are trying to test, the inputs, the results that should be produced by those inputs, and how we actually get ready for and run the tests. In this section we are looking at three things: test conditions, test cases, and test procedures, or scripts. They are described in the sections below. Test conditions are documented in a test design specification. We will look at how to choose test conditions and prioritize them. Test cases are documented in a test case specification. Test procedures are documented, as you may expect, in a test procedure specification, also known as a test script or a manual test script. Test analysis is the process of looking at something that can be used to derive test information. This basis for the tests is called a test basis. It could be a system requirement, a technical specification, the code itself, for structural testing, or a business process. Sometimes tests can be based on an experienced user's knowledge of the system, which may not be documented. The test basis includes whatever the tests are based on. From a testing perspective, we look at the test basis in order to see what could be tested. These are the test conditions. A test condition is simply something that we could test. If we are looking to measure coverage of code decisions, branches, then the test basis would be the code itself, and the list of test conditions would be the decision outcomes, true and false. If we have a requirement specification, the table of contents can be our initial list of test conditions. For example, if we are testing a customer management and marketing system for a mobile phone company, we might have test conditions that are related to a marketing campaign, such as age of customer, preteen, teenager, young adult, mature, gender, postcode, or ZIP code, and purchasing preference, pay-as-you-go or contract. A particular advertising campaign could be aimed at male teenaged customers in the Midwest of the USA on pay-as-you-go, for example. When identifying test conditions, we want to throw the net wide to identify as many as we can, and then we will start being selective about which ones to take forward to develop in more detail and combine into test cases. We could call them test possibilities. As we cannot test everything, we have to select a subset of all possible tests. In practice, the subset we select may be a very small subset, and yet it has to have a high probability of finding most of the defects in a system. We need some intelligent thought processes to guide our selection. Test techniques, i.e. test design techniques, are such thought processes. A testing technique helps us select a good set of tests from the total number of all possible tests for a given system. Different techniques offer different ways of looking at the software under test, possibly challenging assumptions made about it. Each technique provides a set of rules or guidelines for the tester to follow in identifying test conditions and test cases. The test conditions that are chosen will depend on the test strategy or detailed test approach. For example, they might be based on risk models of the system, likely failures, compliance requirements, expert advice, or heuristics. Test conditions should be able to be linked back to their sources in the test basis. This is called traceability. Traceability can be either horizontal through all the test documentation for a given test level, e.g. system testing, from test conditions through test cases to test scripts, or vertical through the layers of development documentation, e.g. from requirements to components. Why is traceability important? Consider these examples. The requirements for a given function or a feature have changed. Some of the fields now have different ranges that can be entered. Which tests were looking at those boundaries? They now need to be changed. How many tests will actually be affected by this change in the requirements? These questions can be answered easily if the requirements can easily be traced to the tests. A set of tests that has run okay in the past has started to have serious problems. What functionality do these tests actually exercise? Traceability between the tests and the requirement being tested enables the functions or features affected to be identified more easily. Before delivering a new release, we want to know whether or not we have tested all of the specified requirements in the requirement specification. We have a list of the tests that have passed. Was every requirement tested? Having identified a list of test conditions, it is important to prioritize them so that the most important test conditions are identified before a lot of time is spent in designing test cases based on them. It is a good idea to try and think of twice as many test conditions as you need, then you can throw away the less important ones, and you will have a much better set of test conditions. Note that spending some extra time now while identifying test conditions doesn't take very long, as we are only listing things that we could test. This is a good investment of our time. We don't want to spend time implementing poor tests. Test conditions can be identified for test data as well as for test inputs and test outcomes. The next step would be to convert a test condition to a test case. Test conditions can be rather vague, covering quite a large range of possibilities. However, when we come to make a test case, we are required to be very specific. In fact, we now need exact and detailed specific inputs, not general descriptions, e.g. Jim Green, age 17, living in Grand Rapids, Michigan, with credit of $8.64. Expected result, add to Q4 marketing campaign. Note that one test case covers a number of conditions: teenager, male, Midwest area, pay as you go, and credit of less than $10. For a test condition of an existing customer, the test case input needs to be Jim Green, where Jim Green already exists on the customer database, or part of this test would be to set up a database record for Jim Green. A test case needs to have input values, of course, but just having some values to input to the system is not a test. If we don't know what the system is supposed to do with the inputs, we can't tell whether our test has passed or failed. In order to know what the system should do, we need to have a source of information about the correct behavior of the system. This is called an oracle, or a test oracle. The next step is to group the test cases in a sensible way for executing them, and to specify the sequential steps that need to be done to run the test. For example, a set of simple tests that cover the breadth of the system may form a regression suite, where all of the tests that explore the working of a given functionality or feature in depth may be grouped to be run together. Some test cases may need to be run in a particular sequence. For example, a test may create a new customer record, amend that newly created record, and then delete it. These tests need to be run in the correct order, or they won't test what they are meant to test. The document that describes the steps to be taken in running a set of tests and specifies the executable order of the tests is called a test procedure, and is often also referred to as a test script. It could be called a manual test script for tests that are intended to be run manually rather than using a test execution tool. Test script is also used to describe the instructions to a test execution tool. An automation script is written in a programming language that the tool can interpret. This is an automated test procedure. The test procedures, or test scripts, are then formed into a test execution schedule that specifies which procedures are to be run first, a kind of superscript. The test schedule would say when a given script should be run, and by whom. The schedule could vary depending on newly perceived risks affecting the priority of a script that addresses that risk. For example, the logical and technical dependencies between the scripts would also be taken into account when scheduling the script. For example, a regression script may always be the first to be run when a new release of the software arrives, as a smoke test or sanity check. Returning to our example of the mobile phone company's marketing campaign, we may have some tests to set up customers of different types on the database. It may be sensible to run all of the setup for a group of tests first. So our first test procedure would entail setting up a number of customers, including Jim Green, on the database. As shown in the table below, a test script has the following columns: 1. Test case ID 2. Step ID 3. Step description 4. Test data 5. Expected outcome. Writing the test procedure is another opportunity to prioritize the tests to ensure that the best testing is done in the time available. A good rule of thumb is find the scary stuff first. However, the definition of what is scary depends on the business, system, or project. For example, is it worse to raise Bob founder's credit limit when he is not a good credit risk? He may not pay for the credit he asked for, or to refuse to raise his credit limit when he is a good credit risk? He may go elsewhere for his phone service, and we lose the opportunity of lots of income from him. The next topic to discuss is test design techniques. There are many different types of software testing technique, each with its own strengths and weaknesses. Each individual technique is good at finding particular types of defect and relatively poor at finding other types. For example, a technique that explores the upper and lower limits of a single input range is more likely to find boundary value defects than defects associated with combinations of inputs. Similarly, testing performed at different stages in the software development life cycle will find different types of defects. Component testing is more likely to find coding logic defects than system design defects. Each testing technique falls into one of a number of different categories. Broadly speaking, there are two main categories: static and dynamic. Static techniques were discussed in Chapter 3. Dynamic techniques are subdivided into three more categories: specification-based, black box, also known as behavioral techniques; structure-based, white box, or structural techniques; and experience-based. Specification-based techniques include both functional and non-functional techniques, i.e., quality characteristics. The first of the dynamic testing techniques we will look at are the specification-based testing techniques. These are also known as black box or input/output driven testing techniques because they view the software as a black box with inputs and outputs, but they have no knowledge of how the system or component is structured inside the box. In essence, the tester is concentrating on what the software does, not how it does it. Notice that the definition mentions both functional and non-functional testing. Functional testing is concerned with what the system does, its features or functions. Non-functional testing is concerned with examining how well the system does something, rather than what it does. Non-functional aspects, also known as quality characteristics or quality attributes, include performance, usability, portability, maintainability, etc. Techniques to test these non-functional aspects are less procedural and less formalized than those of other categories, as the actual tests are more dependent on the type of system, what it does, and the resources available for the tests. Structure-based testing techniques, which are also dynamic rather than static, use the internal structure of the software to derive test cases. They are commonly called white box or glass box techniques, implying you can see into the system, since they require knowledge of how the software is implemented, that is, how it works. For example, a structural technique may be concerned with exercising loops in the software. Different test cases may be derived to exercise the loop once, twice, and many times. This may be done regardless of the functionality of the software. In experience-based techniques, people's knowledge, skills, and background are a prime contributor to the test conditions and test cases. The experience of both technical and business people is important, as they bring different perspectives to the test analysis and design process. Due to previous experience with similar systems, they may have insights into what could go wrong, which is very useful for testing. Let us discuss when to apply which test design technique. Specification-based techniques are appropriate at all levels of testing, component testing through to acceptance testing, where a specification exists. When performing system or acceptance testing, the requirement specification or functional specification may form the basis of the tests. When performing component or integration testing, a design document or low-level specification forms the basis of the tests. Structure-based techniques can also be used at all levels of testing. Developers use structure-based techniques in component testing and component integration testing, especially where there is good tool support for code coverage. Structure-based techniques are also used in system and acceptance testing, but the structures are different. For example, the coverage of menu options or major business transactions could be the structural element in system or acceptance testing. Experience-based techniques are used to complement specification-based and structure-based techniques, and are also used when there is no specification, or if the specification is inadequate or out of date. This may be the only type of technique used for low-risk systems, but this approach may be particularly useful under extreme time pressure. In fact, this is one of the factors leading to exploratory testing. In testing a program, you are limited to trying a small subset of all possible inputs, of course. Then, you want to select the right subset, the subset with the highest probability of finding the most errors. One way of locating this subset is to realize that a well-selected test case also should have two other properties. 1. It reduces, by more than a count of 1, the number of other test cases that must be developed to achieve some predefined goal of reasonable testing. 2. It covers a large set of other possible test cases. That is, it tells us something about the presence or absence of errors over and above this specific set of input values. These two properties, although they appear to be similar, describe two distinct considerations. The first implies that each test case should invoke as many different input considerations as possible to minimize the total number of test cases necessary. The second implies that you should try to partition the input domain of a program into a finite number of equivalence classes such that you can reasonably assume, but, of course, not be absolutely sure, that a test of a representative value of each class is equivalent to a test of any other value. That is, if one test case in equivalence class detects an error, all other test cases in the equivalence class would be expected to find the same error. Conversely, if a test case did not detect an error, we would expect that no other test cases in the equivalence class would fall within another equivalence class. Since equivalence classes may overlap one another, these two considerations form a black box methodology known as equivalence partitioning. The second consideration is used to develop a set of interesting conditions to be tested. The first consideration is then used to develop a minimal set of test cases covering these conditions. An example of an equivalence class in the triangle is the set 3 equal valued numbers having integer values greater than 0. By identifying this as an equivalence class, we're stating that if no error is found by a test of one element of the set, it is unlikely that an error would be found by a test of another element of the set. In other words, our testing time is best spent elsewhere in different equivalence classes. Test case design by equivalence partitioning proceeds in two steps. 1. Identifying the equivalence classes, and 2. Defining the test cases. Identifying the equivalence classes. The equivalence classes are identified by taking each input condition, usually a sentence or phrase, in the specification, and partitioning it into two or more groups. You can use the following table to do this. Notice that two types of equivalence classes are identified. Valid equivalence classes represent valid inputs to the program, and invalid equivalence classes represent all other possible states of the condition, i.e., erroneous input values. Given an input or external condition, identifying the equivalence classes is largely a heuristic process. A set of guidelines is as follows. 1. If an input condition specifies a range of values, for example, the item count can be from 1 to 999, identify one valid equivalence class, one less than item count less than 999, and two invalid equivalence classes, item count less than 1 and item count greater than 999. 2. If an input condition specifies the number of values, for example, 1 through 6 owners can be listed for the automobile, identify one valid equivalence class, and two invalid equivalence classes, no owners, and more than 6 owners. 3. If an input condition specifies a set of input values, and there is reason to believe that the program handles each differently, type of vehicle must be bus, truck, taxicab, passenger, or motorcycle, identify a valid equivalence class for each, and one invalid equivalence class, trailer, for example. 4. If an input condition specifies a must-be situation, such as first character of the identifier must be a letter, identify one valid equivalence class, it is a letter, and one invalid equivalence class, It is not a letter. If there is any reason to believe that the program does not handle elements in equivalence class identically, split the equivalence class into smaller equivalence classes. The second step is the use of equivalence classes to identify the test cases. The process is as follows. 1. Assign a unique number to each equivalence class. 2. Until all valid equivalence classes have been covered by, incorporated into, test cases, write a new test case covering as many of the uncovered valid equivalence classes as possible. 3. Until your test cases have covered all invalid equivalence classes, write a test case that covers one, and only one, of the uncovered invalid equivalence classes. The reason that individual test cases cover invalid cases is that certain erroneous input checks mask or supersede other erroneous input checks. For instance, if the specification states enter book type, hardcover, softcover, or loose, and amount, 1999, the test case XYZ0, expressing two error conditions, invalid book type and amount, will probably not exercise the check for the amount, since the program may say XYZ is unknown book type and not bother to examine the remainder of the input. As an example, assume that we are developing a compiler for a subset of the Fortran language, and we wish to test the syntax checking of the dimension statement. The specification is listed below. In the specification, items in italics indicate syntactic units, for which specific entities must be substituted in actual statements. Brackets are used to indicate option items, and an ellipsis indicates that the preceding item may appear multiple times in succession. The first step is to identify the input conditions, and, from these, locate the equivalence classes. These are tabulated in Table 4.1. 1. The first input condition would be number of array descriptors. Valid equivalence classes for this would be 1 and greater than 1. There is no invalid class for this input condition. 2. The second input condition would be size of array name. Valid input class for this will be any number between 1 to 6. Invalid classes for this would be 0 and any number greater than 6. 3. The third one would be array name. Valid equivalence for this one would be array name with numbers and array name with letters. Invalid class would be array name with anything other than digits and letters. In similar way, we can identify the equivalences classes for all the input conditions. The important thing here is to identify both the positive and negative classes. Experience shows that test cases that explore boundary conditions have a higher payoff than test cases that do not. Boundary conditions are those situations directly on, above, and beneath the edges of input equivalence classes and output equivalence classes. Boundary value analysis differs from equivalence partitioning in two respects. 1. Rather than selecting any element in an equivalence class as being representative, boundary value analysis requires that one or more elements be selected such that each edge of the equivalence class is the subject of a test. 2. Rather than just focusing attention on the input conditions, input space, test cases are also derived by considering the result space, output equivalence classes. Few general guidelines for boundary value analysis are as follows. 1. If an input condition specifies a range of values, write test cases for the ends of the range and invalid input test cases for situations just beyond the ends. For instance, if the valid domain of an input value is 1.0 plus 1.0, write test cases for the situations 1.0, 1.0, 1.001, and 1.001. 2. If an input condition specifies a number of values, write test cases for the minimum and maximum number of values, and one beneath and beyond these values. For instance, if an input file can contain 255 records, write test cases for 0, 1, 255, and 256 records. 3. Use guideline 1 for each output condition. For instance, if a program computes the monthly FICA deduction, and if the minimum is $0 and the maximum is $1,165.25, write test cases that cause $0 and $1,165.25 to be deducted. Also, see if it is possible to invent test cases that might cause a negative deduction or a deduction of more than $1,165.25. Note that it is important to examine the boundaries of the result space because it is not always the case that the boundaries of the input domains represent the same set of circumstances as the boundaries of the output ranges, e.g., consider a sign subroutine. Also, it is not always possible to generate a result outside of the output range, but it is worth considering the possibility, nonetheless. 4. Use guideline 2 for each output condition. If an information retrieval system displays the most relevant abstracts based on an input request, but never more than 4 abstracts, write test cases such that the program displays 0, 1, and 4 abstracts, and write a test case that might cause the program to erroneously display 5 abstracts. 5. If the input or output of a program is an ordered set, a sequential file, for example, or a linear list, or a table, focus attention on the first and last elements of the set. 6. In addition, use your ingenuity to search for other boundary conditions. Let's take the example of the triangle analysis program to illustrate the need for boundary value analysis. For the input values to represent a triangle, they must be integers greater than 0 where the sum of any two is greater than the third. If you are defining equivalent partitions, you might define one where this condition is met and another where the sum of two of the integers is not greater than the third. Hence, two possible test cases might be 3-4-5 and 1-2-4. However, we have missed a likely error. That is, if an expression in the program were coded as a plus b greater than equals c instead of a plus b greater than c, the program would erroneously tell us that 1-2-3 represents a valid scalene triangle. Hence, the important difference between boundary value analysis and equivalence partitioning is that boundary value analysis explores situations on and around the edges of the equivalence partitions. The techniques of equivalence partitioning and boundary value analysis are often applied to specific situations or inputs. However, if different combinations of inputs result in different actions being taken, this can be more difficult to show using equivalence partitioning and boundary value analysis, which tend to be more focused on the user interface. The other two specification-based techniques, decision tables and state transition testing, are more focused on business logic or business rules. A decision table is a good way to deal with combinations of things, e.g., inputs. This technique is sometimes also referred to as a cause-effect table. The reason for this is that there is an associated logic diagramming technique called cause-effect graphing, which was sometimes used to help derive the decision table. Decision tables aid the systematic selection of effective test cases and can have the beneficial side effect of finding problems and ambiguities in the specification. It is a technique that works well in conjunction with equivalence partitioning. The combination of conditions explored may be combinations of equivalence partitions. The first task is to identify a suitable function or subsystem. that has a behavior which reacts according to a combination of inputs or events. The behavior of interest must not be too extensive, i.e. should not contain too many inputs, otherwise the number of combinations will become cumbersome and difficult to manage. It is better to deal with large numbers of conditions by dividing them into subsets, and dealing with the subsets one at a time. Once you have identified the aspects that need to be combined, then you put them into a table listing all the combinations of true and false for each of the aspects. Take an example of a loan application, where you can enter the amount of the monthly repayment, or the number of years you want to take to pay it back, the term of the loan. If you enter both, the system will make a compromise between the two, if they conflict. The two conditions are the loan amount and the term, so we put them in a table. There will be two conditions for this case. 1. Repayment amount has been entered. 2. Term loan has been entered. Next we will identify all of the combinations of true and false, see Table 4.3. With two conditions, each of which can be true or false, we will have 4 combinations, 2 to the power of the number of things to be combined. Note that if we have 3 things to combine, we will have 8 combinations. With 4 things, there are 16, etc. The next step, at least for this example, is to identify the correct outcome for each combination. In this example, we can enter one or both of the 2 fields. Each combination is sometimes referred to as a rule. So we have 2 actions or outcomes. 1. Process loan amount. 2. Process term. At this point, we may realize that we hadn't thought about what happens if the customer doesn't enter anything in either of the 2 fields. The table has highlighted a combination that was not mentioned in the specification for this example. We could assume that this combination should result in an error message, so we need to add another action, see table. This highlights the strength of this technique to discover omissions and ambiguities in specifications. It is not unusual for some combinations to be omitted from specifications, therefore this is also a valuable technique to use when reviewing the test basis. The final step of this technique is to write test cases to exercise each of the 4 rules in our table. In this example we started by identifying the input conditions, and then identifying the outcomes. However, in practice it might work the other way around. We can see that there are a number of different outcomes and have to work back to understand what combination of input conditions actually drive those outcomes. The technique works just as well doing it in this way, and may well be an iterative approach as you discover more about the rules that drive the system. State transition testing is used where some aspect of the system can be described in what is called a finite state machine. This simply means that the system can be in a finite number of different states, and the transitions from one state to another are determined by the rules of the machine. This is the model on which the system and the tests are based. Any system where you get a different output for the same input, depending on what has happened before, is a finite state system. A finite state system is often shown as a state diagram. For example, if you request to withdraw $100 from a bank ATM, you may be given cash. Later you may make exactly the same request, but be refused the money because your balance is insufficient. This later refusal is because the state of your bank account has changed from having sufficient funds to cover the withdrawal to having insufficient funds. The transaction that caused your account to change its state was probably the earlier withdrawal. A state diagram can represent a model from the point of view of the system, the account, or the customer. A state transition model has 4 basic parts. 1. The states that the software may occupy, open/closed, or funded/insufficient funds. 2. The transitions from one state to another. Not all transitions are allowed. 3. The events that cause a transition, closing a file, or withdrawing money. 4. the actions that result from a transition, an error message, or being given your cache. Note that in any given state, one event can cause only one action, but that the same event, from a different state, may cause a different action and a different end state. We will look first at test cases that execute valid state transitions. In deriving test cases, we may start with a typical scenario. A sensible first test case here would be the normal situation, where the correct PIN is entered the first time. To be more thorough, we may want to make sure that we cover every state, i.e., at least one test goes through each state, or we may want to cover every transition. A second test, to visit every state, would be to enter an incorrect PIN each time, so that the system eats the card. We still haven't tested every transition yet. In order to do that, we would want a test where the PIN was incorrect the first time, but okay the second time, and another test where the PIN was correct on the third try. These tests are probably less important than the first two. Note that a transition does not need to change to a different state, although all of the transitions shown above do go to a different state. So there could be a transition from access account, which just goes back to access account, for an action such as request balance. Test conditions can be derived from the state graph in various ways. Each state can be noted as a test condition, as can each transition. Coverage of all individual transitions is also known as zero switch coverage, coverage of transition pairs is L switch coverage, coverage of transition triples is 2 switch coverage, etc. Deriving test cases from the state transition model is a black box approach. Measuring how much you have tested, covered, is getting close to a white box perspective. One of the advantages of the state transition technique is that the model can be as detailed, or as abstract, as you need it to be. Where a part of the system is more important, that is, requires more testing, a greater depth of detail can be modeled. Where the system is less important, requires less testing, the model can use a single state to signify what would otherwise be a series of different states. Deriving tests only from a state graph, also known as a state chart, is very good for seeing the valid transitions, but we may not easily see the negative tests, where we try to generate invalid transitions. In order to see the total number of combinations of states and transitions, both valid and invalid, a state table is useful. The state table lists all the states down one side of the table, and all the events that cause transitions along the top, or vice versa. Each cell then represents a state event pair. The content of each cell indicates which state the system will move to when the corresponding event occurs while in the associated state. This will include possible erroneous events, events that are not expected to happen in certain states. These are negative test conditions. So, for example, if the system is in state 1, inserting a card will take it to state 2. If we are in state 2, and a valid PIN is entered, we go to state 6 to access the account. In state 2, if we enter an invalid PIN, we go to state 3. We have put a X in the cells. That should be impossible, i.e., they represent invalid transitions from that state. We have put a question mark for 2 cells, where we enter either a valid or invalid PIN when we are accessing the account. Perhaps the system will take our PIN number as the amount of cash to withdraw. It might be a good test. Use case testing is a technique that helps us identify test cases that exercise the whole system on a transaction-by-transaction basis from start to finish. A use case is a description of a particular use of the system by an actor, a user of the system. Each use case describes the interactions the actor has with the system in order to achieve a specific task, or, at least, produce something of value to the user. Actors are generally people, but they may also be other systems. Use cases are a sequence of steps that describe the interactions between the actor and the system. Use cases are defined in terms of the actor, not the system, describing what the actor does and what the actor sees rather than what inputs the system expects and what the system outputs. They serve as the foundation for developing test cases mostly at the system and acceptance testing levels. Use cases can uncover integration defects, that is, defects caused by the incorrect interaction between different components. Used in this way, the actor may be something that the system interfaces to, such as a communication link or subsystem. The PIN example that we used for state transition testing could also be defined in terms of use cases, as shown in table. We show a success scenario and the extensions, which represent the ways in which the scenario could fail to be a success. Actor is the person who is working on the system and system is the application under test. So the use case flow will be as below. 1. Actors inserts the card in the ATM. 2. System validates the card and asks for PIN 3. Actor inserts the PIN and so on. Structure-based techniques serve two purposes: test coverage measurement and structural test case design. They are often used first to assess the amount of testing performed by tests derived from specification-based techniques, i.e., to assess coverage. They are then used to design additional tests with the aim of increasing the test coverage. Structure-based test design techniques are a good way of generating additional test cases that are different from existing tests. They can help ensure more breadth of testing, in the sense that test cases that achieve 100% coverage in any measure will be exercising all parts of the software from the point of view of the items being covered. Test coverage measures in some specific way the amount of testing performed by a set of tests, derived in some other way, e.g. using specification-based techniques. Wherever we can count things, and can tell whether or not each of those things has been tested by some test, then we can measure coverage. The basic coverage measure is coverage is equal to number of coverage items exercised divided by total number of coverage items multiplied by 100, where the coverage item is whatever we have been able to count and see whether a test has exercised or used this item. Test coverage can be measured based on a number of different structural elements in a system or component. Coverage can be measured at component testing level, integration testing level, or at system or acceptance testing levels. For example, at system or acceptance level, the coverage items may be requirements, menu options, screens, or typical business transactions. Other coverage measures include things such as database structural elements, records, fields, and subfields, and files. At integration level, we could measure coverage of interfaces or specific interactions that have been tested. The call coverage of module, object, or procedure calls can also be measured. We can measure coverage for each of the specification-based techniques as well. EP, percentage of equivalence partitions exercised. We could measure valid and invalid partition coverage separately if this makes sense. BVA, percentage of boundaries exercised. We could also separate valid and invalid boundaries if we wished. Decision tables, percentage of business rules or decision table columns tested. State transition testing. There are a number of possible coverage measures. First, percentage of states visited. Second, percentage of valid transitions exercised. Third, percentage of pairs of valid transitions exercised. Fourth, percentage of invalid transitions exercised from the state table. The coverage measures for specification-based techniques would apply at whichever test level the technique has been used, e.g. system or component level. When coverage is discussed by business analysts, system testers, or users, it most likely refers to the percentage of requirements that have been tested by a set of tests. This may be measured by a tool such as a requirements management tool or a test management tool. However, when coverage is discussed by programmers, it most likely refers to the coverage of code, where the structural elements can be identified using a tool, since there is good tool support for measuring code coverage. Statements and decision outcomes are both structures that can be measured in code, and there is good tool support for these coverage measures. Code coverage is normally done in component and component integration testing. For most practical purposes, coverage measurement is something that requires tool support. However, knowledge of the steps typically taken to measure coverage is useful in understanding the relative merits of each technique. Our example assumes an intrusive coverage measurement tool that alters the code by inserting instrumentation. 1. Decide on the structural element to be used, i.e. the coverage items to be counted. 2. Count the structural elements or items. 3. Instrument the code. 4. Run the tests for which coverage measurement is required. 5. Using the output from the instrumentation, determine the percentage of elements or items exercised. Instrumenting the code. Step 3 implies inserting code alongside each structural element in order to record when that structural element has been exercised. Determining the actual coverage measure. Step 5 is then a matter of analyzing the recorded information. In common with all structure-based testing techniques, code coverage techniques are best used on areas of software code where more thorough testing is required. Safety-critical code. Code that is vital to the correct operation of a system, and complex pieces of code are all examples of where structure-based techniques are particularly worth applying. The first type of coverage that we will be discussing is statement coverage. Statement coverage could be measured as number of statement exercised divided by total number of statements multiplied by 100. Studies and experience in the industry have indicated that what is considered reasonably thorough black box testing may actually achieve only 60% to 75% statement coverage. Typical ad hoc testing is likely to be around 30%. This leaves 70% of the statements untested. Different coverage tools may work in slightly different ways, so they may give different coverage figures for the same set of tests on the same code, although at 100% coverage they should be the same. We will illustrate the principles of coverage on code. For example, consider code below. Although it isn't completely correct, we have numbered each line, and will regard each line as a statement. Some tools may group statements that would always be executed together in a basic block which is regarded as a single statement. However, we will just use numbered lines to illustrate the principles of coverage of statements. Lines. Let's analyze the coverage of a set of tests on our 6-statement program. Which statements have we covered? In test 1.1, the value of C will be 8, so we will cover the statements on lines 1 to 4 and line 6. In test 1.2, the value of C will be 50, so we will cover exactly the same statements as test 1.1. In test 1.3, the value of C will be 49, so again we will cover the same statements. Since we have covered 5 out of 6 statements, we have 83% statement coverage with 3 tests. What test would we need in order to cover statement 5, the one statement that we haven't exercised yet? Since we have covered 5 out of 6 statements, we have 83% statement coverage with 3 tests. What test would we need in order to cover statement 5, the one statement that we haven't exercised yet? How about this one? Test 1.4, A equals 20, B equals 25. This time the value of C is 70, so we will print large C, and we will have exercised all 6 of the statements. So now statement coverage equals 100%. Notice that we measured coverage first, and then designed a test to cover the statement that we had not yet covered. Note that test 1.4 on its own is more effective towards our goal of achieving 100% statement coverage than the first 3 tests together. Just taking test 1.4 on its own is also more efficient than the set of 4 tests, since it has used only 1 test instead of 4. Being more effective and more efficient is the mark of a good test technique. A decision is an if statement, a loop control statement, e.g. do while or repeat until, or a case statement, where there are 2 or more possible exits or outcomes from the statement. With an if statement, the exit can either be true or false, depending on the value of the logical condition that comes after if. With a loop control statement, the outcome is either to perform the code within the loop or not, again a true or false exit. Decision coverage is calculated by decision coverage is equal to number of decision outcomes exercised divided by the total number of decision outcomes multiplied by 100. Let's suppose that we already have the following test, which gives us 100% statement coverage for above code sample test set to test 2.1, A equals 20, B equals 15. Which decision outcomes have we exercised with our test? The value of C is -10, so the condition, C less than 0, is true, so we will print C negative, and we have exercised the true outcome from that decision statement. But we have not exercised the decision outcome of false. What other test would we need to exercise the false outcome and to achieve 100% decision coverage? Test set to test 2.1, A equals 20, B equals 15. Test 2.2, A equals 10, B equals 2. This now covers both of the decision outcomes, true, with test 2.1, and false, with test 2.2. The next topic is experience-based testing techniques. The first one that we are going to discuss is error guessing. Error guessing is a technique that should always be used as a complement to other more formal techniques. The success of error guessing is very much dependent on the skill of the tester, as good testers know where the defects are most likely to lurk. Some people seem to be naturally good at testing, and others are good testers because they have a lot of experience, either as a tester or working with a particular system, and so are able to pinpoint its weaknesses. This is why an error guessing approach, used after more formal techniques have been applied to some extent, can be very effective. In using more formal techniques, the tester is likely to gain a better understanding of the system, what it does, and how it works. With this better understanding, he or she is likely to be better at guessing ways in which the system may not work properly. There are no rules for error guessing. The tester is encouraged to think of situations in which the software may not be able to cope. Typical conditions to try include division by 0, blank, or no input, empty files, and the wrong kind of data, e.g. alphabetic characters where numeric are required. If anyone ever says of a system, or the environment in which it is to operate, that could never happen, it might be a good idea to test that condition, as such assumptions about what will and will not happen in the live environment are often the cause of failures. A structured approach to the error guessing technique is to list possible defects or failures and to design tests that attempt to produce them. These defect and failure lists can be built based on the tester's own experience, or that of other people, available defect and failure data, and from common knowledge about why software fails. The next experience-based technique we will be discussing is exploratory testing. Exploratory testing is a hands-on approach in which testers are involved in minimum planning and maximum test execution. The planning involves the creation of a test charter, a short declaration of the scope of a short 1 to 2 hour time-box test effort, the objectives, and possible approaches to be used. The test design and test execution activities are performed in parallel, typically without formally documenting the test conditions, test cases, or test scripts. This does not mean that other, more formal testing techniques will not be used. For example, the tester may decide to use boundary value analysis, but will think through and test the most important boundary values without necessarily writing them down. Some notes will be written during the exploratory testing session so that a report can be produced afterwards. Test logging is undertaken as test execution is performed, documenting the key aspects of what is tested, any defects found, and any thoughts about possible further testing. A key aspect of exploratory testing is learning by the tester about the software, its use, its strengths, and its weaknesses. As its name implies, exploratory testing is about exploring, finding out about the software, what it does, what it doesn't do, what works, and what doesn't work. The tester is constantly making decisions about what to test next, and where to spend the limited time. This is an approach that is most useful when there are no or poor specifications, and when time is severely limited. It can also serve to complement other, more formal testing, helping to establish greater confidence in the software. In this way, exploratory testing can be used as a check on the formal test process by helping to ensure that the most serious defects have been found. So after discussing all these techniques, we come to the point where we have to choose one of them to apply in a particular scenario. Let's look at the factors that go into the decision about which techniques to use when. Which technique is best? Each technique is good for certain things, and not as good for other things. For example, one of the benefits of structure-based techniques is that they can find things in the code that aren't supposed to be there, such as Trojan horses or other malicious code. However, if there are parts of the specification that are missing from the code, only specification-based techniques will find that structure-based techniques can only test what is there. If there are things missing from the specification and from the code, then only experience-based techniques would find them. Each individual technique is aimed at particular types of defect as well. For example, state transition testing is unlikely to find boundary defects. The choice of which test techniques to use depends on a number of factors, including the type of system, regulatory standards, customer or contractual requirements, level of risk, type of risk, test objective, documentation available, knowledge of the testers, time and budget, development life cycle, use case models, and previous experience of types of defects found. Some techniques are more applicable to certain situations and test levels, others are applicable to all test levels. This chapter has covered the most popular and commonly used software testing techniques. With so many testing techniques to choose from, how are testers to decide which ones to use? Perhaps the single most important thing to understand is that the best testing technique is no single testing technique. Because each testing technique is good at finding one specific class of defect, using just one technique will help ensure that many, perhaps most, but not all, defects of that particular class are found. Unfortunately, it may also help to ensure that many defects of other classes are missed. Using a variety of techniques will therefore help ensure that a variety of defects are found, resulting in more effective testing. So how can we choose the most appropriate testing techniques to use? The decision will be based on a number of factors, both internal and external. The internal factors that influence the decision about which technique to use are models used. Since testing techniques are based on models, the models available, i.e. developed and used during the specification, design, and implementation of the system, will to some extent govern which testing techniques can be used. For example, if the specification contains a state transition diagram, state transition testing would be a good technique to use. Tester knowledge/experience, how much testers know about the system and about testing techniques will clearly influence their choice of testing techniques. This knowledge will in itself be influenced by their experience of testing and of the system under test. Likely defects, knowledge of the likely defects will be very helpful in choosing testing techniques, since each technique is good at finding a particular type of defect. This knowledge could be gained through experience of testing a previous version of the system, and previous levels of testing on the current version. Test objective, if the test objective is simply to gain confidence that the software will cope with typical operational tasks, then use cases would be a sensible approach. If the objective is for very thorough testing, then more rigorous and detailed techniques, including structure-based techniques, should be chosen. Documentation, whether or not documentation, e.g. a requirement specification, exists, and whether or not it is up to date will affect the choice of testing techniques. The content and style of the documentation will also influence the choice of techniques. For example, if decision tables or state graphs have been used, then the associated test techniques should be used. Life cycle model. A sequential life cycle model will lend itself to the use of more formal techniques, whereas an iterative life cycle model may be better suited to using an exploratory testing approach. The external factors that influence the decision about which technique to use are risk. The greater the risk, e.g. safety critical systems, the greater the need for more thorough and more formal testing. Commercial risk may be influenced by quality issues, so more thorough testing would be appropriate, or by time to market issues, so exploratory testing would be a more appropriate choice. Customer/contractual requirements. Sometimes contracts specify particular testing techniques to use, most commonly statement or branch coverage. Type of system. The type of system, e.g. embedded, graphical, financial, etc., will influence the choice of techniques. For example, a financial application involving many calculations would benefit from boundary value analysis. Regulatory requirements. Some industries have regulatory standards or guidelines that govern the testing techniques used. For example, the aircraft industry requires the use of equivalence partitioning, boundary value analysis, and state transition testing for high-integrity systems, together with statement, decision, or modified condition decision coverage depending on the level of software integrity required. Time and budget. Ultimately, how much time there is available will always affect the choice of testing techniques. When more time is available, we can afford to select more techniques, and when time is severely limited, we will be limited to those that we know have a good chance of helping us find just the most important defects.